Well, hello, everyone. My name is Guy Royce, and with me today is...
Hello, Justin Castilla here.
We're here. Welcome to Redis Monthly Live. You might be wondering why we call it Redis Monthly Live. And, well, the reason we call it Redis Monthly Live is because we do it live, like right now. We do it every month, and we talk about Redis. So it's a very, very, very imaginative name because, I scored extra points in creativity when I was in elementary school. So. So how you doing today, Justin?
Good. I'm excited to be here, excited to learn. Lots of cool topics today.
Yeah, we do have some cool topics. Let me bring them up here so everyone else can see them. So we've got two speakers today. We've got Stephen Lorello. I keep calling him Stephen, but he just goes by Steve. I guess I'm channeling his mom. I don't know. He's going to be talking about Bitwise Operations in Redis, which I think is a really cool and sort of, it's kind of a dense feature that a lot of people don't get into, but it's got a lot of potential. It's really interesting. It's fun. And so he's going to hopefully, as he says, unmask that today. And then we also have Barry Stahl. Barry is he's a friend of mine. He's someone I've known for a long time from the conference circuit. He's going to be talking about some patterns from reliable systems using microservices, and he's going to be using some Redis streams to show us how to do that. So that's what we've got on for today. Before we bring them on to give their talks, so it'll be Stephen first and then Barry. Of course, we want to pay the bills here. And just give a little shout out here to the people who actually make this possible. Justin and I both work for Redis, and we love it if you use Redis no matter how you use it. But an easy way to use Redis is use Redis Enterprise Cloud. It's free to try. The entry level plans are very working in my garage, sort of inexpensive. So go check it out at redis.com/try-free. And if your Redis is sitting in the cloud, you don't have it running on your machine. So you may not have the Redis CLI command line tool handy and ready. And so check out Redis Insight. It's a GUI for Redis that you can run locally. So go check those out. And then with that, I think it's time to bring in our special guests. Let's see if I can do that here. If I can actually make the technology work. Let's bring in Stephen and Barry. They're waving crazily. They're so excited.
How you doing?
So welcome, everyone. How you doing?
Good.
Fantastic. Happy to be here.
Yeah. So normally this is the part where I ask like some inane question to get a conversation going. But I am sorely unprepared, and I do not have a random question to get the conversation going. So, hey, Justin, do you have a random question to get the conversation going? I did not ask Justin this in advance.
I like the idea that this is a Redis Wizards convention. That's kind of cool like that.
Oh, the wizard's name is Zinkerby. Which is one of our Redis commands, Z Inkerby. Zinkerby the wizard. He lives in the village of Hinkerby and is fighting the dragon's members. So
I'm definitely Wizard Stralgo.
Yeah. Stralgo is the barbarian who also is fighting the dragon.
If anybody is scratching their head right now, what Guy and Justin are using are just random Redis commands that actually sound like different characters from the D&D game.
It's fun to pronounce the Redis commands. Like you got the S union for set union, and it's Sun Ion clearly, right?
Sun Ion.
And S members, set members is Smembers, right? That sounds like the name of a dragon. It's kind of got Ember in there. It kind of sounds fiery. So this is one of the fun things that we do. So Barry, Stephen, you want to do quick introductions just to let everyone know who you are and why we should care? You can go in either order. You can fight.
You're first, Stephen. Go. Or Steve. Sorry.
All right. So, hey everyone, I'm Steve Morello. Like Guy said, only my mother and my wife call me Stephen, so I usually just go by Steve.
And apparently me now too. Yeah. So
apparently Guy. I am the .NET developer advocate here at Redis. I've been in engineering now for going on 8 years. And before going into advocacy, I worked on GPS systems and air traffic control systems and video conferencing systems. So I'm excited to be here today to talk to you all about Bitwise Operations, because we used quite a bit of it in when we were doing signal processing for satellites. So some really cool applications of it.
Cool.
Well, and I'm Barry Stahl. I'm a solution architect at Carbona. That's this right here. And I'll do a little bit better intro when I start speaking, but just a little teaser. I'm the guy that keeps a list of his favorite physicists and favorite mathematicians, but not my favorite wizards. So, you'll have to make that, what it is. And you'll see some of that when I get on the stage here.
Now, Barry, because you brought the car elevator to the meetup, does that mean that Guy, Justin, and I all get a free car from the car elevator?
For the vending machine?
Yeah,
I would like one of those too. So why don't we'll put in a request and see what comes up.
Sounds good.
Right.
I'll give them a week of free Redis consulting if they'll give me a car. That'd be fantastic.
Very good deal.
That'd be a great deal, actually. Well, depending on the car. Yeah.
Some ultra-lucky.
It's like, here's your 1996 Saturn. Yeah.
We don't put those in the vending machine.
The vending machine. Nice.
Well, excellent. Well, let's go ahead and let's get this party started. So, Stephen, are you ready?
I'm ready.
Okay, I'm going to go ahead and turn you on here, and we'll hide in the background here. So, floor is yours, Stephen.
Sounds good. So, hey everyone. As I said, I'm Steve Lorello. I'm a developer advocate at Redis, and I'm going to be unmasking Bitwise Operations with you all today. So let's start off with a question. What are Bitwise Operations? Bitwise Operations are operations that are performed between two strings of bits. You essentially go bit by bit through each string, and you apply the relevant operation to them. So there's a bunch of examples of Bitwise operators out there, and usually they'll essentially correspond to like different VHDL gates, which are like very low level gates in computing. But some examples, more common ones, are ands, ors, XORs, nots, a left shift, and a right shift. An and, you essentially goes bit by bit through the string, and you check each bit. If both bits are 1, you set it to 1. If 1 is 1 and 1 is 0, you set it to 0. And if both are 0, you set it to 0. So essentially, both bits have to be 1 in order for it to come out 1. For ORs, it's either bit. For XORs, it's exactly 1 bit, and NOT will actually invert the bit string. So in this example, 1100 NOT yield 0011. Now, left shifts and right shifts take the first operand and they shift it by the number in the second operand. So if you have a 1 and you shift it to the left 2, you get 100, which in binary comes out to 4. So this 1 shifted 2 becomes 4. And then again, if this is 4, shifted 2 to the right becomes 1. So bitwise operations are supported in Redis. The AND, OR, XOR, and NOT are all supported by the bitop command. And then the left and the right shifts are supported, but they're supported implicitly through the Bitfield command, which is a really rich and dense command that you can really get into using. So let's look at an example of something we might want to use a bitwise operation for. Say we have a piece of telemetry that we have a ton of equipment all over the world, essentially generating telemetry all the time. Now, say we only have 3 fields in there. We have a longitude, a latitude, and an instrument. And say we want to store that all in Redis, so we have some centralized repository where it's all stored. Well, if we use the Redis hash to maintain it, we would have a longitude field, a latitude field, and an instrument ID field. All 3 of those fields would be 32-bit numerics. And that means in the best case, you'd have around 96 bits that you're storing all of that data in. And where that becomes a problem isn't necessarily if you have 1 or 2 records that are stored in there, but if you have many, many, many records, essentially that just increases by 96 bits at a time. And if you can like millions of different records, it could be a lot of data. And you can actually constrain that by using a bit field. So essentially, let's say we decided that we can get enough precision from our longitude and latitude in 26 bits. And then for our instrument IDs, each instrument is just going to have a 8-bit ID. So longitude, you could store in bits 0 to 25 of that string. Latitude, you could store in bits 26 to 51 of that string. And then 52 to 59 can store the ID bits. And in this case, we're saying that a latitude and longitude are just 26-bit fixed point integers, fixed point numbers. They have 1 bit of sign, 9 bits of for the integer, 16 bits for the decimal, and that's it. So what this actually looks like, this bitmap, if we drill down into it even further, 0 to 9 is the longitude's int, 10 to 25 is the longitude's decimal, 26 to 35 is the latitude's int, 36 to 51 is the latitude's decimal, and then 52 to 59 are the ID. Now, let's take an example of this. If we wanted to store, say, this piece of telemetry here. So we have a longitude of negative 122.0641, latitude of 37.3772, and an ID of 5. Now, if anyone wanted to pop into Google Maps and look at that, that's actually Redis's headquarters, or a somewhat granular look at Redis's headquarters. It's only 4 bits of precision as opposed to, I think, 6 is what Google Maps uses. So if we wanted to set the longitude for this, we could essentially have a single key that we're going to store everything in, and we'll call that telemetry. We use the bitfield command, telemetry, and then we set an I10, so a signed 10-bit integer, starting at the offset 0 to negative 122. So that takes care of that 122-bit. We can then set U16 starting at the offset 10 to 641, which is the decimal port of this. And you can go and do the same thing for latitude, both the integral and the decimal portion of it. And then finally, for the ID, you can set this field at the offset of 52, which is, if we go all the way back here, is the beginning of the ID, set that to 5. And so you can go through and you can set all of these up in 5 different steps. Or if you want to do this locally, if you want to compute all these bits locally, you can come up with one giant number. So in this case, we have U60 of this enormous number right here, and just set it all at once. So both will produce a logically equivalent result. Now, if we wanted to query the telemetry, we can go one at a time through, and we can do gets on all of these. So we use the bitfield command, telemetry get. If we want to get an I10, we get the I10 starting at 0. That would produce that negative 122. For the decimal, we can do a U16 at 10. That would produce a decimal. We would have to then make sure that we're representing it correctly because this is a fixed point precision. You'd probably have to pad this with a 0 on the left side just so you get the 0641 instead of the 641. And then the same thing for the telemetry for the latitude and the integral and decimal and the ID. Essentially, you can just go in and just get these bits of data out of here. And in this case, we're storing all of this in 60 bits as opposed to, 96 bits for the hash. So it's compressed about to 2/3 the size, a little less than 2/3 the size of the original hash. Now, another way we can retrieve these things and potentially even store like a contemporaneous version of what the current telemetry is by using masks. So if we have a particular bit field where we're storing like the current latitude, current longitude, current ID of the most recent instruments report, we can do that using masks. So what are masks? And this actually comes in the unmasking part. Masks are strings of bits that allow you to represent a highlighted portion of a substring of bits. They're often the right operand in a bit operation. So let's take our 60 bits of telemetry again. We have these fields and what those fields represent, but then we need to come up with a mask for them. So because this is 0 to 25 and a 60-bit bit field, this mask is going to be 26 bits of ones followed by 34 bits of zeros. So it's going to be a 60-bit number as 25 bits of one or 26 bits of ones followed by zeros. That allows you to mask the Bitfield and just pull out the longitude. Same thing with latitude, but instead, this is only a 34-bit strings with 26 bits of ones, and the instrument ID is 8 bits of ones, and it doesn't have any zeros in the end because it's the end of the string. So we can then go ahead and go into Redis and say a Bitfield, set up a longitude mask, a latitude mask, and an ID mask, and those just will persist in Redis. And there are U60s with the particular value. And then you can just use the bitop command to actually and those out and maybe store the telemetry masked by the longitude mask, telemetry masked by the latitude mask, and telemetry masked by the ID mask into like a current longitude, current latitude, current ID. It's a simple example. It's a somewhat contrived example. But this is really quite commonly used in signal processing for pulling out different bits and telemetry gathering. So if we want to get the current longitude, so if we stored it in there, we can pull out the current longitude by getting a U26 at number 0. So number in this case is the number of U26s you're going to go into the bit field. Same thing with latitude. That's a number. So we're going 1 U26 in, and we're pulling out that U26. And then we can pull out the current ID with the U8 starting at 52. So yeah, that was my talk on bit operations. You can find out more about bit operations at Redis University. RU 101 has a section on bit ops, which is pretty cool. And you can read more about the bit operations on redis.io. That's it.
Excellent. Thanks a lot, Steve. I did it this time. I called you Steve instead of Steven.
There we go.
Soon I will be all trained up. So let's see here. Figure out which buttons I got to click to bring in all the people. So there was actually a comment during your talk. It was nothing satisfies my brain more than Bitwise Operations. So
I love Bitfields.
You've got a fan.
Yeah.
You got a fan. There was another thing in here I wanted to point out here. So I'm not going to attempt to pronounce your name here, but someone asked a very important question of Barry when we were sort of rambling on earlier. No, not that one. That one. If your list of favorite scientists and physicists and stuff, is Stephen Wolfram on the list?
Stephen Wolfram is not at the moment on the list. I'm considering. So anyone involved in quantum anything, but quantum field theory in particular, is fascinating stuff. Not someone I've just. He's not someone that I've been seriously exposed to his work. I probably need to remedy that.
Yeah. So his alpha is fantastic.
I get that.
So, excellent. So thanks for asking. Does anyone have any questions for Steve while we're here answering some questions, everything before we get on to the next thing? So that's always a dangerous thing to ask because there's a lag, and then I have to wait 30 seconds for someone to actually respond with the question. So, I've paused uncomfortably long enough. Wait. Cool. Ignoring memory constraints. Why else would you consider using Bitwise Operations in regards to your example of GPSS?
So, like GPS systems, now there is a publicly available spec you can go look at. But essentially, the GPS system, the full positioning system, just broadcasts down waveforms and as waves of energy down to the Earth. And inside the waveform is actually embedded all the navigation data that you need. That has the position. Actually, position is a very important thing that it has in there. It has a very exact time too that is based off the atomic clocks and those things. And it doesn't have it's not going to just transmit down text. Right? It's going to transmit down something that can really be used and interpreted by really low-level components that are going to pull things out of the signal. So, people write essentially hardware to parse those signals and do it at a hardware level, and that's actually extremely useful. And the telemetry example that I used here was, what if you have a wide array of different instruments that you have around the world, and you want to be able to send it all into a centralized location. You don't want it to blow up your memory. That's where like that memory constraint. That's where Redis gets really nice for using data operations.
Excellent. I think that's our only question. So I think we'll hand it over to Barry now. Everyone cool? Do you got anything else you need or want to say, Steve? Steve?
Nope, I'm good.
Okay, well, thank you very much. Up next, we have Barry. Let me go ahead and share your screen here. Barry's going to, I believe, do a more formal introduction that may or may not involve physicists. So
it most definitely will.
Okay.
Awesome. Thanks, guy.
Floor is yours, Steve, or Barry.
Stephen is fine. Stephen is actually my middle name, so just so you know. So thank you. I am Barry Stahl. I'm a solution architect for Carbona. I'm based in Phoenix, Arizona, where it is absolutely beautiful outside right now, and I should really be presenting from out there instead of trapped in here. But for now, this will work. And as I mentioned, I do have a list of my favorite physicists and favorite mathematicians. So I do love talking about this. I love adding people to the list. So please feel free to tweet at me about it. Tell me who should or shouldn't be on here. My Twitter handle is bsstall, and that should be on the screen. Please hit me up with that. This list is, or at least a link to this list is pinned on my Twitter account. Grace Hopper, absolutely, 100%. One of the absolute heroes of our industry. So, cool. Let's see. All right. So I did mention I'm at Carbona and paying the bills a little bit here. We are hiring. We're growing tremendously. It is an amazing place to work. So I hope you consider coming and joining us. This link will take you to our job site. So please feel free to check it out, see what's available, and come do amazing things with us. This link will also be at the end with all of the links and all of the references from this talk. I'm also an open source contributor. I contribute to a number of open source projects. None of those are particularly relevant here, so I won't go into them, but they are linked in the slide deck that you'll have access to at the end. And finally, I am one of the founders of Arizona GiveCamp. So if you're not familiar with a GiveCamp, they're all over the world. It's a weekend event where we bring a bunch of software creators, developers, designers, project managers, etc., put them all in a room together with a bunch of local charities, and we code for those charities over the weekend, and we turn the code over to them at the end of the week, and hopefully have helped them, or end of the weekend, and hopefully have helped them further their mission. So it's quite an amazing experience. And as our friend Rob Richardson likes to say, sleep is optional, caffeine is provided. So be sure to check out givecamp.org and see if there's one in your area. All right, let's get into the meat of the talk here. For this, we're going to use a simple example. We're going to use an example of doing two things, an application that needs to do two things. In this simple example, it's going to need to send an email and write to a database. But this could be any two operations, really. So the idea is just to think about it in terms of the fact that it's trying to do two different things. And that's going to be the example we're going to carry throughout this presentation. And it might look something like this. We have a web service that is called from a website, and that website, that web service does these multiple things. We're going to talk about how to go about making that happen. And this is what it might look like in code. Most of my examples will be C# code, but if you squint really well, this could also be JavaScript code, right? Or just about any other, or Java, just about any semicolon curly brace language. And of course, all of the things we're talking about today apply to just about any scenario, any language, any stack. These concepts are going to apply. So what we've got here is we've got a method, perhaps a web method called from a web service. And it does two things. It sends the email and it updates a database. And you'll have to trust me on this for now, although the code is all up on GitHub and you'll be able to pull it down. There's links in the slide deck. This code actually does all the, it does a lot of the right things. It traps for errors, does multiple retries, and if it still fails after multiple retries, it's going to throw an exception. So what that ends up doing is it ends up basically resulting in the following possible outcomes. We can have a situation, this is our happy path is first, and that's when all tasks succeed and everything's great. So we get the nice green smiley face and all is good. But we can have a couple of other situations as well. We can have the first task fail, or we can have the first task succeed, but the second task fail. Now, in this scenario, the way I've written it, if the first task fails, it's never going to go on to the second task. So we don't have all four. If you had, two combinations of two, you'd normally have four possible outcomes. That third one is invalid because if we do the first thing and it fails, we don't even get to the second thing in this case. So if task A fails, we haven't done anything, but we haven't done anything. So we're in a known state. We failed, but we know exactly what happened. The real dangerous situation is when task A succeeds, but task B fails. So in this case, we've sent an email, maybe an email off to a customer saying, hey, we're doing the thing you asked us to do. And then the database update fails. And then what? That's a dangerous situation. And we can end up causing ourselves real problems when these kinds of things happen. So what do we do about that? Well, there's a common reaction to that is to say, well, what about if we put the database operation into a transaction? So we start off, the very first thing here is that we do a create transaction. We begin that transaction, and then we send the email at that point. And then if the email is successful, we commit the transaction. This is pretty common. I've seen this a lot. I've done this a few times. And it comes from this misunderstanding about the way transactions work and our service level agreements work. So let's look at this. What is it actually doing? Well, what it really does is instead of making it just having three possible negative outcomes, we've kind of split the middle one. We still have our happy path. So we still have the green smiley when everything works. But the middle scenario where the first task fails, because now the first task is the begin transaction. If that fails, or if the email send fails, we're in the same situation. We haven't really done anything, because if the email send fails, nothing's gone out, we'll roll back the database transaction. So we haven't written anything, we haven't sent anything. We're okay. Those two middle non-green smiley faces. It's not an ideal situation, but we haven't done anything, so we're still in a known state. And again, the bad situation is when A and B succeed, but C fails. And now you might think, but how often is C going to fail? Because task C in this scenario is the database commit. So we started a transaction, we sent our email, and now all we have to do is commit to a database. That really can't fail, right? Well, the problem is it can, and is not only it not only can fail, but it's actually more likely to fail. Because what happens is our SLAs for pretty much any dependency you get, including Redis, by the way, are all based on time, not number of transactions. So the fact that we're doing a single transaction instead of two different things, or instead of just the one, or combining them into a single thing, doesn't really matter as much as the fact that that is open a lot longer. That transaction is active for a much longer period of time. So the fact that it's active longer actually makes it more likely to fail. And you have since you have so much more opportunity for it to fail, the question then becomes, well, when did it fail and what did we do during that? Did we send the email or not? Since it's, we may or may not know, if it fails and we roll back, we still don't, we're in that same unknown state. Did we send the email or not? So that's a really dangerous situation. And we'll talk more about why that's dangerous. So what we really end up with is we need to retry at the client, but we have all of these different possibilities. And now I've included all 4 possibilities in this scenario, where we can either continue or what I call roll back, which basically means throw up an exception and let the client retry. We're in that kind of we have these 4 different scenarios here. And I want to point out 2 of them that are fairly common. The one that's rollback if A fails and continue if B fails, that's kind of a logging scenario. What that says is we're going to, if the important task, sending the email or doing whatever it is, writing to a database, that's the one we care about. And if that works, we're okay. But if not, we're just going to ignore the second part. So if the second part is maybe logging, right? We don't want to fail to a client if our logging didn't work. We want to know about it. So we're going to want to do some kind of alerting or monitoring somehow on that. But we don't want to fail for the client. We're still okay in our processing if that logging fails. So in this case, we're ignoring the failure on the second one, but the first one's the one that matters. So this scenario is okay. That's the second column here. This is the first of the yellow columns. The other yellow column is that we're going to roll back if either task fails. And in that scenario, what ends up happening, if assuming we're going to roll back and it's going to retry from the client, so from the thing calling this, it's going to retry. What we end up with there is that if the first task succeeds, but the second one fails and we roll back, we're going to end up retrying. We're going to double tap that first task. So if that first task is sending an email and then the second task fails, like updating the database, we roll back, the client tries again later on, maybe, and what ends up happening is that email gets sent again. So what's important here is that second task must be idempotent. And we'll talk more about what that means later on. So the key to this, and I drill into this more when I have a lot more time, because there's a lot to it here. But the gist of it is we cannot make 2 reliable changes to the system in a single context, a single execution context. It can't be done. And I realize I haven't proven that yet, and nor will I be able to on this call. But know that I believe this, that you simply cannot reliably make more than one change to system state in a single execution context. You can do it. You can make 2 changes if the first change is idempotent, meaning we can do it over and over and over again, and I'll drill into what that really means in a second. Or if the second change is unreliable, like that logging scenario. If we don't really care so much about whether that second task happens, then we're okay because we just ignore that and move on. But you can't reliably make 2 changes. So let's talk about the details here. What is idempotence, first of all? Idempotence is the ability to execute a task some arbitrary number of times greater than or equal to 1, and have the system state be the same. So, for example, it's kind of the canonical example out of Wikipedia is these European train controls, the start and stop buttons. If you hit that green button, you hit that start button the first time and the train's not running, it's going to start the train up. You hit it again, nothing's going to happen. The train is going to remain in a started state. So that button is an idempotent operation because you can hit it as many times you want and it's the same as hitting it once. Another thing that is another idempotent operation is a database upsert. If you send the same data to a database that includes the key, by the way, it has to include the key. But if you send the same thing on an insert or an update, and you continually send that over and over and over again, as long as you send the same data in the same key and it respects that key, then you have an idempotent operation because you can do that as many times as you want and the system is not going to change state. That could be important later. So then what we end up with is an anti-pattern. An anti-pattern that's called the dual write anti-pattern. So what is a dual write? What does that mean? And why is that a problem? Well, a dual write is an attempt to make more than one reliable change to the state of a system in a single invocation. So we've tried to do more than one thing within a single instance. Now, there are some words in here that require further definition, so let's drill into them a little bit. When I say reliable, what I mean is it could be expected to occur exactly once, irrespective of the reliability of the execution environment or the reliability of any dependencies. So we basically take into account, we know that all our dependencies can fail. We know our systems, the hardware that it's running on can fail. And we still make it so that at least the 4, 5, 9s, whatever our reliability metrics are, it happens exactly once, one and only one time. By change here, I mean an atomic modification. So if we're making multiple changes to multiple tables in a database, as long as we do it within a transaction, taking into account that the longer the transactions are, the more chance there is of failure, that's a single modification. Same thing from the perspective of our application for making a web API call or sending a message, say, to a streaming service, something like that. So a single modification is something that's an atomic change to the system state. And by invocation, this is kind of the hardest to define, but ultimately it's an automated response to a signal. So the simplest way to think about it is a call to a web service. Within a single call to that web service, we should be doing one and only one thing, and we can only do one and only one thing reliably. Same thing for, say, a user action or something like this. If we try and do multiple things, they're not going to be reliable by this definition of reliable. I'm hoping that makes sense. I don't see any questions in the chat, but feel free to drop any questions in there or let me know if something I'm saying doesn't make sense or if I need to go back and revisit something. All right. Here's why this is so important. These particular kinds of failures are nightmares when it comes to reliability because they manifest themselves in so many different ways. They're just unpredictable. Are you familiar with the term a Heisenbug? It's one of my favorite old programming jargon. A Heisenbug is, I'm talking about, going back to the physicists metaphor earlier. It's one where when you look at it, when you try and find it, it's no longer there or it's changed. A lot of these will not be repeatable because ultimately what they generally come down to is they resulted from a hardware failure somewhere, and those are generally not repeatable. So you can end up having these things manifest in duplicate data, sending multiple emails. You can have missing data. There's all kinds of things that can go wrong here. And so they're very hard to diagnose, very hard to fix, and very hard to remediate when you find them, because none of your tools, none of your services specifically do that thing that you need to do. What you end up with is basically doing some manual operations every time something like this happens. Hopefully they don't happen too often, but every time you end up doing a manual fix for this. So if you end up having to do lots of one-off database scripts, for example, to update your database and fix data, that's probably a smell that says you may have these kinds of problems in your code. Lots of other things can cause that as well. But so I really try to avoid these kinds of problems, because they're the things that cause you to have to give up your nights and weekends when you're supporting an application. So let's spend the rest of this talk talking about how we can avoid them. And the gist of it is that we need to keep it separate in order to keep it safe. Don't do two things at once. So we're going to look in detail at 3 different patterns that allow us to keep these things separate. And then we'll talk a little bit about sagas, that it's kind of putting it all together in the saga pattern. So let's jump right in to the first of these, which is the transactional outbox pattern. And the goal of a transactional outbox is to reliably update a data store and then trigger an additional downstream action. So in this case, what we're doing is we're updating the data store. Then we're going to go downstream and say, based on that data store update, we're going to send the email. So we make a single atomic write to our database within a transaction, but it's only the one thing. We're only doing that one thing in the initial request. Change the state of the database, so update our state as necessary, but also within that transaction, we're writing a command. And that command is what's going to be used to trigger the downstream operation, in this case, sending the email. So let's take a quick look and see what that looks like using SQL Server as our data store. So I am going to pull up some code, and just for reference, all of this code I mentioned is available on GitHub. This is the exact code that we're going to be looking at today. It's all out there, and it's linked in the slide deck. So you'll have this link again at the end. Go back into the transaction here and bring up some code. All right. So this is the solution in Visual Studio, and this diagram is it's a sequence diagram of what is actually going to happen here. So what we're going to do is our user is going to issue a request, and so our use case here is that the user is a customer that's saying, hey, I would like you to do something. And so what we're going to do is we're going to have an email responder that is going to send them an email that says, yep, we got your request and we're working on it. And of course, we have to capture the request so we know we can do stuff with it. So it looks like this. The user issues the request to a request service, and you'll see that request service is over here. And I just clicked into it when I didn't intend to. Issues the request to the request service. The request service pushes that to the SQL Server and gets a response back that says, yes, we've committed that transaction. At the same time, we have an email service running that is looking for those changes. And when it sees an unsent message, it sends the email and confirms that. So let's take a quick look at what that is. And I'm going to drill into this code a little more than I will on the other examples, just to get us. All the rest of them follow the same patterns. They're just different implementations. So in this case, let's start with our request service. We do a bunch of setup, and then we read the email address and the description of the request. In this case, it's going to be off a console. That's going to be our simulation of the customer request. So the customer is going to be able to issue a request by typing it into a console. Not the ideal user experience, but we'll get there. You know, I mean, we have to walk before we run. And then it's going to call this IIssueRequest service and issue the request. The IIssueRequest service is here. And all it's doing is formatting the information and saving the request out. Now, in this case, I said I put the logic to create the email in here. It doesn't have to be. I did it here because that's where it would be if we were doing a dual write. So if we were just putting both the email, send the email, and update the database all in one place, it would all be here or in somewhere that's referenced from here. So that's why it's I put that in here. So it saves the request, and this is where it's going to do the transaction to write out both of them. So what you're seeing here is I begin the transaction here inside the SQL connection, and it updates two tables: TBL requests, that's the state table, and then TBL messages. This is our email table. This is our outbox table. This is the one that says take the downstream action. And then it says that that's been saved. So let's jump in and look at the email service very quickly. This will, also be running. So this service, it runs on demand, right? Whenever we, whoops, I didn't mean to click that either. Whenever a customer makes a request, we spin this up and do the work. The email service is running in the background. So this is a true service. It's sitting in the background, watching for these requests to come in, and then doing the work. So again, this one is sort of a subscription based. So we have a process async method here after doing a bunch of setup that subscribes by basically looping until it's canceled. It loops, calls get unsent messages. So that's basically calling a SQL repository that's going to go out and say, do I have any messages waiting? Do I have any that are unsent? If no, it's just going to return null, and I'll ignore it. I'll actually log that no messages were queued. I'll log that in a debug so it won't show up in production, but we'll see it because I have it configured to log debug messages. And then if it does have one, then it does the work of calling the email client to send the message. So pretty straightforward. We issue the request using the request service. We push that out to the database. Two different tables, one with the state update that we can use later for the rest of our process, and one with the command to send the email. So how does that look when we're doing it here? All right, this is that code compiled and ready to run. And when we issue our request, we'll issue the request from some guy at surelynotourguy.com. And the request is going to be, please power down your 3D printers when not in use. So let's go ahead into the code and run our email service so we can see this in operation. Okay. All right, so that message processing is starting over there. And you can see that right now it knows that there are no messages that are queued to be sent. And if we go ahead and submit this request, it pushes that up to the database, and our monitoring tool finds it and goes ahead and sends out the email. And if I go back into my email here, where I have it all filtered out nicely, you can see that we just got a Your request with tracking ID so-and-so was received and will be processed as soon as possible. This is really crappy customer service, but you'll do better. All right. You know that guy? Cool. Good to know. And if there's any questions, please throw them in the chat. All right. So the outbox pattern has several advantages. It's good in that you can quickly persist your data. And this is actually something I'll harp on a couple of times as we go through this talk. The first thing you want to do is persist when you get a request in, persist it as quickly as you can. Get it safe, get it on disk. And then once you've got it safe, then other things, you're less likely to have a problem. So it does that fairly quickly, although it is putting it in a transaction, which, as we mentioned before, is slower, more likely to fail. But it does allow you to quickly persist that information. It also captures every update. Not every pattern that we look at today is going to capture every update. We'll talk about that more in the next section on change data capture. And it's very familiar to people. Relational databases are comfortable and familiar, and we know how to use them. So it has that advantage going for it. But it does also have several disadvantages to some of the others that we're going to talk about today. It's not a simple process to scale it or to fan it out. So if you're going to scale it, you have to do all the appropriate things. Like if you're going to create another version of, say, the email service, so that you can have so you can scale and make sure that you can handle your customer load. You have to put all the locking and stuff in there yourself. You have to make sure that only one instance of a processor can get it. Otherwise, you end up sending multiple emails to your customers again. It's also harder to fan out than other patterns. But by that, I mean, it's harder to use this to do another thing. Like if we wanted to then also trigger the downstream operation that actually does the work, we would probably have to add another column to our database or add another command that's another table to our database. So you have to make fairly significant changes to allow it to fan out to multiple processes as well. Some of the other patterns we're going to look at today do this much better. But for a simple operation, something that's just, we get the data, we persist it, we do the one thing downstream, this is a very good, and we're not going to have to scale a lot. This is a very good thing to do. But it's also using the database as a queue. And we have better tooling for that. Databases really should be used for persisting data. You could make a case that a queue is a type of persistence, but it's a different type of persistence. It has a different purpose. And as I mentioned, it adds some weight to that persistence by doing this, because now instead of just making one update, we're making two within a transaction. So it's a heavier update. And then, like all of these operations, it is still susceptible to errors on commit. So now think about what this does. In fact, let me pull back up the sequence diagram. When we, this is the Redis one, but it's going to be very similar. I'll get the right one up. And so, by the way, these sequence diagrams are right there. There's drawings right in the code here. And if you have the plant UML extensions in your environment, you can see these, or you could just go and paste these into websequencediagrams.com or something like that and be able to see these diagrams. When we find that we have a message that we need to handle, we send the message, And then we still have to write we still have to do a commit to the database that says we got this, and we're writing it out. We've sent it. So we still have something of that commit problem. We've just made it much, much smaller and much less likely to fail. But that problem still exists. And we're never going to be able to fully get rid of it. But there are better ways to handle that don't that are reducing the risk here. So this is best. The outbox pattern is actually best for idempotent operations, like all things. And idempotent operations are going to be very important. We're going to talk a lot more about those as we go through. All right. Let's keep going here. Again, if there's any questions on the outbox pattern or any of these things, please throw them in the chat. Let's go on to our second pattern. This is change data capture. Change data capture, the goal of it is to reliably update a data store and trigger an additional action. Now, if that goal sounds familiar to you, good, because that's also the goal of the outbox pattern. Update a data store, trigger a downstream action. All three of these first patterns are going to be very, very similar. And in fact, if you look at the sequence diagrams, they're going to be very, very similar. The difference here is that we're going to make the same kind of atomic write to a data store, but we're only going to write one thing. We're only going to write our change to the data store. And then the data store is going to use its log and the features of that data store to actually trigger the secondary operation. So this is a very similar pattern. The difference is the database itself is capturing the update and pushing it out to the downstream process. So let's take a look at that. And for that, we're going to use the example of Cosmos DB. So here is the same exact thing using Cosmos DB. The biggest difference here is that Cosmos will actually push these changes. Well, the Cosmos SDK will push the changes into our code. And Cosmos actually does a really, really nice job of managing the implementation for us. So it handles a lot of this, and we'll see what that means here in just a second. So let's take a quick look at the differences here in this code. So our request service is almost identical. The difference being we have additional configuration here to configure our Cosmos DB instance. And then we still read the request off of the console and then issue the request. And in this case, the issuer of the request calls save request on a Cosmos repository. And here's where it writes out that one thing. So it just has to write the one in this case. In the previous one, we had to write to 2 tables and put it in a transaction. In this case, all we're doing is doing the create item async here to create that document in our document store. Cosmos DB is a document store in case you're not familiar with it. So we're going to write that out, and then we're going to depend on the features of Cosmos, the change data capture features, to push that down to our email service. So let's take a quick look at that. Again, we have additional configuration here for Cosmos, and now we're actually running this in a host. So we're going to just sit there, and it's going to be spinning through and waiting for updates from the Cosmos SDK. Here's our change monitor. And what this does is here in the execute async method, it's actually creating the instance of the change feed processor. So Cosmos and the Cosmos SDK have this change feed concept. So, and the reason we have it is because this is a distributed database. So if you think about it, a database, all databases today have logs, and they're all based on writing updates to logs. And that's how they do replication and things like that. They do log shipping to move the information around between instances. Those logs can also be used to find out what has changed. And that's what change data capture does, is it looks at those logs and says, whenever there's a change, push out some information. So in this case, what we're saying is I give it a reference to the process message async method, which is right here. And so this change feed, this client is going to call this method whenever it gets a message, whenever it gets an update. And the update itself is going to be in this object, and it's going to be an instance of that document. So whatever the document was changed to, we're going to get that. And that's going to come down in here in our change. Now, with ours, we're only writing commands out there. We're writing events, so we're never changing the documents. If you are actually updating documents, one of the disadvantages here is that you may not get all of the different changes. What you'll get is the last change that occurred during that time period. We'll talk more about that as we get into the advantages and disadvantages here. So when we get a message, we call process async, which is the thing that's actually going to send the email out. So let's see this in action. Now we go to number 2 here. And in this case, we have an instance of the service that's ready to talk to Shirley, or a request from Shirley, not our guy, at guysrs.com. It says, do your part, please recycle your orcs when done with them. So our service is ready over here on the right side to handle it. This is the email service on the right, the request service on the left. Let's call the request service. And you can see it writes the request out to our Cosmos instance. And there we've just received it on the from the SDK, and we've processed it successfully. And now in our email client, we now have the CDC pattern reply received. Oh, change data capture. Very interesting, very useful. I love this one. I love working with Cosmos in this scenario. Airplane references are always welcome. So the big advantages here are that we persist this one thing, and of course Cosmos is wicked fast. I'm not from Boston, but I have to say that at least once in every talk that I give. You can persist it very quickly. And it's also easy to scale and easy to fan out. So unlike the Outbox pattern, where we had to do all the work to figure out how to make it scale and how to use it for multiple things, Cosmos handles all of this for us. And we'll see this also in the streaming pattern next when we use Redis. That all gets handled through the concept of consumer groups. So you can define a consumer group, and Cosmos will distribute within the consumer group. That's how you scale. So that's how you fan out. So within a consumer group, you're only going to get one copy of each individual message. So if you have multiple consumers within that consumer group, one consumer will get that message. So you can scale out to multiple instances and be able to handle lots more customer requests. You can also create new consumer groups, and those different consumer groups will be for different problems. So each consumer group gets a copy of the message, one copy. So you can have a consumer group for sending the email. You could also have a separate consumer group for doing the actual processing, for example. So it handles all of that for you. And in fact, it handles rebalancing things when new groups come in or new consumers come in the same group. So this makes it pretty easy to do the scale and the fan out. The disadvantages are that it's still not guaranteed. It's not guaranteed to get every update. If you make multiple updates during the time between because it does some polling behind the scenes in the SDK. If you make multiple updates very rapidly, you're likely to only see the last change. Now, you're getting the full state of the document, so very often that doesn't matter. But if you must see every single change, every single state that the database went through, this pattern is probably not for you. You're probably going to want to use the streaming pattern that's next. This all makes sense to everybody, hopefully? Let me know if it doesn't. All right. The third pattern, data streaming. This one, we're going to reliably persist a message and then trigger additional actions downstream. So again, we're very, very close. That is a good point. You don't get delete events. Usually people do soft deletes in Cosmos. So if you're, usually you mark something for deletion. So you know that if you read that record, it's been deleted, and then you usually set a time to life on it, and that handles dealing with that. So thank you, John. So in data streaming, we're going to persist the message, but it's not going to be persisted to a database necessarily. It's going to be persisted to some other store. In this case, it's we're going to use Redis as a streaming target. And we're going to allow that to trigger the downstream actions. So here we make a single atomic write. In this case, it'll be atomic because we'll only do one, or we can do them all together and it'll be atomic that way as well. It makes an update to the message stream, and then we use that stream downstream. That stream downstream, we pick that message up downstream and use that to do the exact same thing we've been doing before. So let's take a quick look at that. Now, you've seen this before. This is exactly the same as the previous one, except that we have Redis that we're using as our streaming target. Our request service pushes the message to Redis, and then we are monitoring the Redis stream to get the message and to do the confirmation, to send out the confirmation email. And all of the same things that I mentioned in the when we were talking about CDC apply here. You have consumer groups that manage the who sees what messages across different clients for fan out and scale and such. So how does that look here in our request service? The configuration is just a little bit different. There's less complexity in setting up Redis than there is Cosmos. So we have a little bit less configuration. We pull the request from the command line and issue that request, which just does a save request on now the Redis repository. And then you can see what we do is we're actually doing the save, adding the item to the stream. Yeah, that's our save, is to create the item, get a Redis database, and add the item to this particular stream that we have configured. Likewise, on the consumer side, so the thing that's consuming the message, our email service, a little bit more configuration, or a little less than Cosmos. And again, we're running inside the host to execute this change monitor that when it subscribes here to the stream, and then whenever it gets a message, again, it's looping until cancellation is requested. And this can be done blocking as well. I think I'm doing it non-blocking, but so in this case, I have a situation. I have it checked to see if there's any messages in here. So I'm using a non-blocking operation here, but there's a blocking one where you don't have to handle that. And if there is a message, we go through and we process those messages. I thought there was a way to do it. Oh, this is just to log. So I did this X pending. I used that command just so I could log and see what pending messages are there in the queue. But then we've already got the collection of messages. We already got the message itself that was sent to us here as part of the consumer. There, messages. And we're looping through the messages collection and processing them. So let's see that in action. And here's our streaming. And oh, I also have, hopefully it didn't disconnect. Yep, here's our Redis instance here. So I'm going to turn on the monitor and we should see things as they're coming through. And so you can see that we're polling and we're looping and executing this xread group to see if there's any messages that are there. Let's create one. So this is some guy at ontheinternet.com, and it's a request to be kind to your DM. Now let's issue that request. And there we go. We pushed it into Redis, and our email service responded to it and sent the email out. And there it is right there. Cool. So, data streaming. Advantages. You can persist very quickly. I'm going to say again, because I feel like I need to say it twice. This is wicked fast. So it persists extremely quickly. Of course, with Redis, depending on how you configure it, whether you're persisting you may need to snapshot or what have you, depending to see, that tells you how reliable it is to survive, say, a system crash or something like that. So be careful there in terms of what am I trying to say here? You want to be aware of the persistence needs of your application. Let me say it that way. But again, it does it wicked fast. And it's also easy to scale and easy to fan out because it uses the consumer groups concept. And in this case, it captures every update. Just about any mechanism you use for doing streaming, whether that's pushing to a message queue like, say, RabbitMQ or something like that, or Kafka or what have you, is going to capture every update and give you the ability to use that. The disadvantages, of course, you do have that concern about the persistence. And again, we still have to do something that commits that. Now, it may be an automatic commit, like it is in this case, kind of commits automatically for us. But you still have that concern about, did it get committed properly, and is that going to be a problem? All right. So as we've said, these patterns are really similar. They always persist the data first, then do something with it. So get it to disk, get it safe, and then take an action. The CDC and streaming patterns are very easy to fan out to n number of tasks. So, they're easy to add tasks onto them later on. That becomes very important as systems scale. And Outbox and streaming are guarantee that all messages are sent, where CDC may not do that depending on your implementation. All of these, of course, are susceptible to errors on commit. So what can we do about that? Well, these patterns get us really close to a large degree of reliability. And this may be, in fact, I think in most cases, it's good enough reliability, as long as we're doing the very minimum of that. It's when we start adding on that we really start making the reliability bad, and also where we start, and more importantly, perhaps, it's where we start getting errors that are difficult to troubleshoot. Because if we're only doing the one thing, if it fails, we're going to know what it is and we know how to fix it. But definitely use idempotence whenever you can. There is no better way to make a system reliable than to make downstream operations idempotent, so that you can just retry them if they fail or if something happens. That said, that's not easy. I could do a whole nother talk on how to make services idempotent. And if you do that, and if you have idempotence at both kind of the consumer, at the producer of the message and the consumer end, what that gives you is exactly once delivery. So that may be possible. The full exactly once delivery all the way through your application may actually be possible. It's also pretty expensive. There's a lot of work that has to go into it. There's a lot of effort that has to be put into it. So use the pattern with caution, but it's there if you really, really need it. All right. For our last bit, we're going to kind of wrap up by pulling it all together and looking at ways of kind of grouping these things together. And there's really two of them that allow you to actually take do larger sets of things. You know, when we've talked about do one thing per instance. And by the way, I should point out that when I say instance, I don't mean the container. So if you have, say, a web service, it can have 10 different methods in it. That doesn't really matter how many web methods there are. It does matter because it makes it harder to deploy. But from a reliability standpoint, I don't care how many web methods you have in a single container. What matters is the execution context. What executes within a single trigger? So I generally think about these things as web methods. That makes the easiest, web service requests, API calls. That's the kind of thing that we're really talking about here. And there's two ways to kind of organize them. There's an orchestration where you have a single controller that basically goes out and kind of has to tell everything, here's what I need you to do. So it's issuing commands and responding to those to the responses to those commands. And that all has to be done in a safe and reliable way. And there's also choreography. And this is my favorite way of doing things because this is, well, we'll see examples of it here. So let's look at orchestration first. This is a fairly simple orchestration. It actually does the first two boxes at the top there, update the data and email responder are actually the pieces that we've been looking at the whole time here. I've added a few things on here, and I'm not going to drill into them in detail right now since we're running out of time. But it might look something like this. And I have sort of queues in there for updating errors and for making the updates for the commands and then the error responses. Those queues, I show them as, and they could be streams, you can think of them as streams. Those streams may be read by only these one thing, or they may be read by by all of the different services. You could do it as a single command stream that all of the services read from. So there's a number of ways of doing these things. But the key to this is you do this when you need to be able to issue like compensating transactions, for example. So our billing service in there is calling out to a bank. Banks are notoriously these days have thin wrappers over legacy mainframe systems. Nothing wrong with that. It's how they are. There's certainly no way to distribute a transaction among them, and you wouldn't want to do a distributed transaction anyways because it destroys scalability. So if we were to issue a request to the billing service, and that would call the bank and debit their account, and then we find out, we get an error back from the request action service that says we can't actually do the thing they asked us to do. We need to issue a compensating transaction on that billing service. And that would be the responsibility of the orchestration service to know that it needs to do that and to issue the command to do it. I'm not a huge fan of orchestrations, but there are times where that's the right thing to do. And I just illustrated one of those times when you need to issue that. You need to be able to issue that compensating transaction. That's one good way of doing it. My preference is to use these choreographies. And the reason for that is because when you end up having each service do one and only one thing, and then you publish the results and then allow other services to know of those results and to take their own actions, what you end up with is a series of very simple, very independent services that all do one thing, do it very well, and do it reliably and work well together. And I like to call that the microservices pattern. And to me, this is the best way to implement a set of microservices. Now, there is a cost that comes along with these things, of course. To me, this is actually a very simple thing. People say, well, this is a lot of additional complexity. Well, there is complexity in the fact that it is there's more boxes and arrows, but each of those services is very simple, very easy to understand. How they work together is kind of complicated, or can be more complicated, but we have really, really good tools these days for doing that. If you're publishing to Azure, for example, App Insights gives you that kind of insight, that kind of information almost for free. Not free, but it's pretty cheap. And you don't have to do anything to get it just about, except tell it instrument your applications. So there's a lot of insight in there that you can get very easily that helps you understand what's going on inside the system. And you'll have to do some things right. You'll have to use, for example, correlation IDs. So when the user issues a request, you're going to want to put a correlation ID on there that carries all the way through, so you can easily trace a request all the way through the system. But if you do those simple things, this is a great way to implement microservices in a very, very reliable, robust way that scales easily and will not cost you your nights and weekends because you have all these Heisenbugs laying about whenever something weird happens. Because weird things won't happen. It'll respond to them. So my most important takeaway for you is when you're building your applications, don't add on. It's very tempting to see a thing. Oh, we've got this service here that's already sending, or it's already writing to the database. I need to send an email. I'm just going to plop the email code right there in with that right before it writes the data out to the database or what have you. And what I hope you take away from this is that is super dangerous, and you're far better off if you can keeping it separate, responding to the database update, ideally with CDC or with a streaming pattern, and working that way rather than cramming another thing into it. Because that's how you end up with these big monoliths, the distributed monolith pattern, you've heard of that, or anti-pattern. That's how you end up with these kind of things. So, in summary, I'm going to start off by saying 100% reliability is impossible. We haven't actually said that here. Hopefully, I've convinced you of that. But you can get much, much closer by avoiding taking 2 actions in a single context. Do everything you can to limit the number of actions you take in a single context. Do that by persisting immediately, then taking other actions, and then using one of these patterns, Outbox, CDC, streaming, to handle the additional actions. And then you can use sagas to coordinate all of that and put them together into a full application. And then do what is that, a slapshot reference? Never, never, never add on. This is old movie reference day. All right. So here's a bunch of resources for you. The most important one at the top, of course, is Carbona. Please click that when you download these slides. There's also the links to the code samples and a bunch of articles that talk about these different patterns and how to use them. You get all of this, and the link is also in the chat. You can go to this and pull down these slides, and then all of that is clickable or printable, and you can do whatever you want. And this QR code does take you to that. So if you just want to shoot the screen right now, hopefully not literally, and grab the slide deck, you'll be able to get to that and see all these resources and read up on all this interesting stuff. That said, I thank you for your attention, and I'll turn it back over to, this time, our guy, definitely our guy.
Surely not our guy, yeah. So I'm going to bring everyone back in and turn your screen off here. So excellent job, Barry. Very insightful. Lots of good stuff there. Redis is hiring too. You looking for work? John says thank you as well, as does Kevin. So, yeah, great job. You mentioned the distributed monolith. I actually have a term for that. I call those polyolithic macroservices.
I don't know.
It sound like it's real, you know, like it. That makes it sound good, right?
It almost sounds important that way. I think you need to make it more wizard-like. Can we work something in there where we make that sort of like some kind of like spell or something where
polyolithic macroservices Expelliarmus. Yeah.
That's the process of getting rid of them. Is that what we were talking
exactly,
about?
Exactly. Yeah. That's how you dispense with those. Okay. And Robert gives you a nice thank you as well. And by the way, I really like your avatar, Robert. That's fantastic. Here's a great question.
Wow, I am so not the right person to. So I'm assuming you're asking from a business perspective. What Carbona does, we are disrupting the used car business, making it easy for you to buy a car from your living room and not have to deal with dealerships, and nobody likes that. And it's an exceptional process, and we have these magnificent. I'm going to move out of the way so you can see them. These things are beautiful. If you haven't seen one, go check one out at sunset, ideally. These car vending machines. So you can have your car delivered to your house or wherever you want. If you don't want it to be delivered, you can come to one of our vending machines and we'll give you a big coin and you get to put it in the vending machine and have your car come out and be delivered to you out of the vending machine. It is quite an experience.
That is so cool.
Yeah. Now, from a technology perspective, we enable all that through the use of our magnificent technology and Redis.
So if I put another coin in there, will I still get just one car? Is an idempotent transaction or not?
I do believe it is idempotent. I'm kind of hoping, but I don't program the vending machines for some reason, because they probably think I would program it to give me a couple of cars. But there's a bunch of Teslas in there that I keep really looking at. But we do have these all over the country. So, if you're near one, check it out. Carbona.com will tell you where they all are.
Excellent. And Jose says he loves Redis live sessions. Thank you. We like them very much too. So thanks for joining the stream. I think that's pretty much all we've got here. Any other questions in the audience before we start with the thanks and the well wishings and all of that? And Jose, I do see your other question there. I think it would be better answered off stream. It's a good question, but it's a little off topic, I think, for us. So I'm gonna punt on that one a little bit. So ask again. Ask me on Twitter, and we can talk about it there. Hey, now that I've said it, I'll go ahead and say, can you talk about this? I don't know a lot about this. It seems slightly off topic to me. What about you, Barry?
So Dapper itself is really just an abstraction mechanism for these things. So you can, you put your application behind Dapper, and that would allow you to switch back and forth between various mechanisms for doing things like, messaging. So say if you wanted to have, a RabbitMQ, and then you say, no, you know what, I'd rather use Redis for streaming, then you can just swap it out and you don't have to change your application code. You just change the configuration of the Dapper service. Orleans and Akka are both actor model implementations that would more be inside your code. And all of them are really useful for building event-driven applications. I'm trying to think, would these patterns still be applicable if you were doing them within the context of the actor model? That's a question I'm not really sure how to answer yet. If you want to ping me on Twitter, I'll come up with a better answer for that.
Excellent. So Jose has another good question, which is what we're going to do next. So let me go ahead and add my screen here to the live stream. So don't miss next month, Redis Monthly Live. It's every third Monday at 2 p.m. Eastern Time, which is 11 a.m. Pacific Time and 7 p.m. in the UK. I just know Eastern Time because that's where I live, and Steve lives there too, so it's all good.
It's a consensus.
Yeah, that's right.
Actually, so next month, Pacific time will be the same. Yeah, that's right. It's Arizona time that'll be different for everybody. So for those of you who are in Arizona, it'll change next month.
Yeah, and it might be next month. The time might be wrong in Europe too, because the U.S. does the time zone change later than Europe does, and then my head explodes. Right. Don't have the speaker lined up completely yet, but we have it scheduled, and we will have a speaker. I've got several speakers I'm talking with, so just a matter of figuring out who it's going to be. So if you want to get notifications of the upcoming Redis Live, just go to meetups.redis.com/RedisLive, and of course you can subscribe to our YouTube channel and follow us on Twitch, and then you'll get notified when we go live. Of course, connect with us. We got a Discord server at discord.gg/Redis. Most of us are on there. I don't think Barry's on there, but Justin and myself and Steve are all on there. And of course, follow us on Twitter. You'll find that out. And we always need speakers. So I've got threads out to about 3 or 4 people right now. But if you're interested in speaking and you're watching, you're watching this later on YouTube, drop me a line. On all the ways you can drop me a line. Probably the easiest way to get a hold of me is just to message me on Twitter at Guy Royce. It's right here in my name. And tell me you're interested in speaking on Redis Monthly Live, and we'll see about getting you scheduled. So always looking for speakers. And that's all we've got here. Here is the big picture of Barry. I'm going to go ahead and turn that off because he's decided that picture is not current enough and does not reflect his gray hair properly. So we'll go ahead and take the screen. So again, thanks everyone for attending, and thanks especially Barry and Steve for presenting today. Without speakers, we don't have a show, and without an audience, the show is pointless. So thanks everyone. Any final words you guys want to say before we kill the stream?
Thanks for paying attention.
Yeah.
So excellent stream, everyone. Thanks a lot. See you all next month.
See ya.